The operational objective was a search and rescue flight under winter pressure. But an irreversible threshold was crossed when two aircraft lost separation while flying in close company. On December 13, 1940, the Royal Canadian Air Force launched a search party from Camp Borden for a missing trainee and his Northrop A-17A Nomad, serial number 3503, overdue from the previous day's training flight. The search unfolded in hard winter conditions, but the official accident record describes the ceiling and visibility as unrestricted at the time of the collision. No whiteout, just clear air under pressure. It came from urgency, cold air, and aircraft working close together while the margins for error collapsed. Two of the search aircraft, including Nomad serial number 3521, were navigating the blind airspace over Lake Muskoka. The two aircraft collided in mid-air, and the flight broke apart in an instant. The Northrop A-17A Nomad was a robust, heavily built military aircraft. Originally designed as an attack platform, the Royal Canadian Air Force utilized the machine for advanced training and target towing operations. The aircraft featured a heavy radial engine and a thick, riveted aluminum structure. When the collision shattered the flight surfaces, these massive components lost all aerodynamic lift. The heavier pieces fell first, lighter fragments lingered, then waterlogged and sank. What mattered is that piece by piece, the wreckage settled through the water column and into the lake's soft-bottom sediments where silt and organic mud began to claim it. The immediate procedural response shifted from rescue to salvage. On January 9, 1941, divers confirmed the location of the first collision aircraft, Nomad 3512. Winter conditions meant working in bitter cold and near-freezing water on Lake Muskoka, sometimes with ice complicating access to the site. At this time, deep underwater work depended on primitive gear, little thermal protection, and air supply that was hard to regulate precisely. Depth and bottom time set the boundary because pressure loads the body with inert gas, driving nitrogen into blood and tissue. Cold then strips core heat and motor control while the clock keeps tightening. A safe return demands staged decompression stops so those gases can vent. Push past the limits in near-freezing water and the failure can be fast and fatal. The 1941 recovery operation pushed these limits until the human system broke. Later accounts report that a diver died during the effort, a stark warning of how narrow their margin had become in cold water, limited equipment, and unforgiving depth. With the hazards escalating and a man lost, authorities abandoned the second search and left Nomad 3521 on the lakebed. This institutional decision initiated a massive operational gap. The wreckage sank deep into the dark, dense mud of the lakebed. The shattered airframe remained unlocated and out of reach on the lakebed. The operational clock was paused and the status transitioned from a rapid salvage mission into a long-term environmental burial. The long gap fundamentally altered the operational nature of the target. When the aircraft was finally confirmed in 2010, it was no longer just a missing airplane. It had become a protected military grave and a highly fragile historical artifact. The deep freshwater environment of Lake Muskoka dictated the wreck's long-term condition over this 72-year period. The freezing temperatures and lack of light slowed organic degradation, while the dense silt slowly consumed the heavier components, pulling them downward into a high-suction mud matrix. Any future engineering team would not simply be pulling metal out of water. They would be executing a delayed forensic extraction, requiring strict evidence discipline and advanced site mapping before a single piece of aluminum could be touched. The long gap meant that historical records, witness accounts, and surface coordinates from 1940 were useless. Before any team could plan a heavy engineering lift, they had to isolate the wreckage from the natural terrain of the lake bottom. The fragmented scatter pattern created multiple false targets across miles of mud, leaving the technical question of how to reliably identify a shattered aluminum airframe in a deep acoustic void. Far beyond any surface observation, the wreckage sat in deep water. The loss event on December 13, 1940 was not an aerodynamic glide to the surface. It was a kinetic mid-air collision that immediately erased the structural integrity of the Northrop A-17A Nomad. When the collision occurred, the kinetic energy exchange instantly overcame the ultimate tensile strength of the aluminum spars and fuselage longerons. The continuous load paths designed to keep the aircraft flying were sheared apart in a fraction of a second. This mechanical failure dictated the entire physical baseline of the wreck site. Mid-air kinetic impacts shatter the structural continuity of an airframe. Instead of a single fuselage ditching intact and remaining localized, the kinetic energy shears the wings, tears the engine mounts, and sections the fuselage. Dense, heavy components immediately decouple from the high-drag aerodynamic surfaces. These distinct objects then descend at radically different rates, drifting outward as they fall through the air in the water column, scattering across a wide footprint rather than a concentrated impact crater. The airframe of Nomad serial number 3521 separated into at least 5 major sections before settling on the bottom of Lake Muskoka. The tail section, the port wing with the main fuselage attached, the starboard wing, the undercarriage, and the radial engine all took separate trajectories to the lakebed. The density of these individual components dictated their final resting geometry and how deeply they penetrated the lake bottom. The heaviest piece of the debris field was the radial engine. Without the buoyancy and drag of the attached wings, this massive block of steel and aluminum plunged straight down, striking the soft, organic mud of the lakebed with maximum kinetic energy. The sheer mass of the engine block concentrated all of its downward force into a small surface area upon impact. This velocity drove the engine deep into the sediment. It became completely buried under 4 feet of dense silt. The mud immediately collapsed back over the impact hole, sealing the engine in a heavy matrix and hiding it entirely from any visual inspection. The lighter wing and fuselage sections fluttered down more slowly, bleeding off energy, as they descended through the water column. They came to rest at a depth of approximately 100 feet. At this depth, the temperature drops drastically and ambient light penetration reaches 0. This environment established the physical parameters for the wreckage over the next 7 decades. The lack of oxygen and the consistent low temperature provided a natural cold water conservation baseline, preventing the severe galvanic corrosion that would have rapidly consumed the thin aviation aluminum in a saltwater marine environment. However, the deep mud environment of Lake Muskoka is not static. Over 70 years, seasonal sediment deposits slowly accumulated over the wreckage. The dense silt continuously enveloped the aluminum surfaces, filling every open compartment, cockpit cavity, and fractured wing root. This long-term settling process slowly equalized the density of the shattered wreckage with the surrounding lakebed terrain. This specific resting geometry is the crucial constraint defining the site. Because the structural integrity was destroyed in the air, the pieces on the lake bottom do not share a single continuous load path. Moving or even identifying one piece does not guarantee the status or location of the others. The port wing and fuselage section, while still partially joined, lay fractured and twisted. The heavy mud forced its way into the crew enclosure, burying the structural ribs and crushing the lighter canopy framing under the weight of the settling silt. The starboard wing lay isolated, its internal fuel tanks ruptured and filled with water and mud, anchoring it firmly to the bottom. The tail section, severed completely at the aft bulkhead, settled into the mud at a different angle, exposing only a fraction of its original surface area to the open water above. This geometry limit meant that any future search team could not rely on finding a single intact shadow on the lakebed. The physical baseline of the wreck was an irregular constellation of sharp, disconnected metal forms, each presenting a different profile to the surrounding environment. The problem became separation, man-made geometry versus the lakebed's own noise. The primary barrier to locating the shattered airframe was not simply the volume of water, but the inherent limitations of acoustic sensors searching across uneven terrain. For decades, the exact position of the wreckage remained entirely unknown. The Ontario Provincial Police Underwater Search and Recovery Unit initiated a specialized operation to systematically eliminate the empty sections of the lake. Their primary tool was side-scan sonar, an instrument towed behind a surface vessel at a specific depth above the lakebed. The device sends high-frequency sound pulses outward, painting a 2-dimensional acoustic image of the bottom. At a depth of approximately 100 feet, the sonar fish had to be flown precisely to avoid colliding with submerged obstacles while staying close enough to the mud to resolve small targets. The operational constraint was the sheer scale of the search zone. To overcome this geographic variable, volunteers brought fresh leads forward in 2007, and the Ontario Provincial Police Underwater Search and Recovery Unit renewed systematic searches beginning in 2008. Searching blind over miles of underwater terrain forces a strict procedural geometry known as grid system mapping. The survey vessel must steer along perfectly parallel tracks, spacing each lane to overlap the previous pass by a heavily calculated margin. This sector sweep pattern guarantees continuous coverage of the lake floor without leaving untested gaps between the acoustic corridors. Or if the boat drifts off the designated line due to surface wind or water currents, the resulting blind spot could easily hide the separated fuselage or the severed tail section of the shattered aircraft. The law enforcement team spent years running these precise lanes, slowly building a comprehensive map of the bottom profile. However, an acoustic return is only as good as the contrast it provides against the background terrain. The complex topography of the lake floor constantly interferes with the return signal, causing a critical sensor limit known as acoustic shadowing. The side-scan sonar paints a picture using reflected sound energy, but when the sound waves hit the leading edge of a natural ridge or a massive boulder, they bounce back strongly while leaving an empty, unmapped void immediately behind the obstacle. The twisted fragments of the aircraft were already partially buried in the deep sediment. These dense metallic pieces can easily hide within these sonar blind spots, appearing on the monitoring screens as nothing more than a natural geological depression or a dense patch of mud. Resolving these shadows required analyzing hundreds of miles of acoustic data across multiple deployment seasons. The Ontario Provincial Police operated with extreme evidence discipline, treating every metallic return as a potential anomaly that demanded secondary verification. Because the mid-air collision had destroyed the structural continuity of the machine, the search teams were not looking for an intact airplane profile. They were hunting for unnatural geometric edges, straight lines, and sharp angles that cast an artificial acoustic shadow against the smooth surrounding silt. After 70 years, the grid work finally produced a definitive target. In the summer of 2010, the sonar mapping identified a cluster of distinct, unnatural structures resting heavily on the mud. Subsequent visual confirmation via dive teams verified the location of the debris field, ending the 70-year search. The acoustic void was finally broken. The geographical coordinates were now a verified fact, firmly locking the physical location of the Northrop airframe into the official record. However, confirming the presence of torn aluminum on a lakebed does not immediately authorize an engineering team to begin extraction. The discovery fundamentally shifted the operational classification of the site. It was now a controlled military site, potentially remains, weapons, and sensitive material. The confirmation of the target triggered a strict sequence of operational decisions. Before any heavy lift could begin, the priority had to be forensic recovery and documentation. In October 2012, Canadian Armed Forces divers retrieved the remains of the 2 missing airmen and recovered 3.30 caliber machine guns from the site, items that helped confirm identity and reduce future handling risk. The completion of this biological and weapons phase fundamentally changed the legal and operational status of the debris field. With the remains, personal effects, and hazardous armaments recovered, military authorities closed the forensic sequence. The recovered biological components were formally transferred to the proper military channels for precise identification and subsequent honors. The site had been systematically downgraded from an active casualty zone to a standardized salvage location. What remained at the bottom of the lake was no longer restricted by forensic protocols. It was now classified strictly as a heavy engineering problem. The fractured fuselage, the isolated wing sections, and the massive radial engine still lay embedded deep within the sediment, waiting for the Air Force engineers. With the site forensically cleared, the engineering challenge pivots to structural extraction against the suction force of the lake bottom. The transition from forensic isolation to heavy engineering introduced a severe mechanical trade-off. The team had to extract 70-year-old corroded aluminum from a dense lake bed without the raw lifting force destroying the exact object they were trying to save. In October 2014, the Royal Canadian Air Force Aerospace and Telecommunications Engineering Support Squadron assumed control of the site. Working alongside Navy divers, the engineering team positioned a commercial barge crane directly over the verified coordinates. because the 1940 mid-air collision had completely erased the structural continuity of the aircraft. The recovery could not be executed as a single unified lift. The team had to treat the debris field as a series of isolated heavy rigging problems, each with a completely unique center of gravity and deeply embedded in the bottom terrain. The primary mechanical constraint of the entire operation was the aircraft power plant. The radial engine was roughly 1,000 pounds in dry weight, depending on the exact variant. However, the vertical kinetic energy of the crash had driven this massive block of steel straight down into the lakebed, penetrating far deeper than the lighter aluminum flight surfaces. It now sat deeply buried in dense organic silt. That burial depth fundamentally changed the lifting physics. Lake mud can form a stubborn suction seal around heavy objects, multiplying the force required to break them free and raising the risk of sudden, damaging shock loads if the seal releases abruptly. To free it without tearing fragile points, divers supervised conservative rigging and incremental lifts. No brute force, just controlled separation until the mud released. With the heaviest and most deeply embedded component safely suspended off the bottom, the engineering team applied the same disciplined load transfer methodology to the rest of the fragmented airframe. The recovery was sequenced deliberately to avoid entangling the separate pieces in the dark water. They brought the aircraft to the surface in several major sections: wings, fuselage components, tail structure, undercarriage parts, and the radial engine were broken free and lifted separately, each rise through the water column treated as its own unstable engineering problem. Breaking the suction seal meant the structure was finally airborne, but the atmospheric exposure clock immediately starts. Breaking the surface of Lake Muskoka immediately replaced a mechanical constraint with a chemical one. The extraction of the 5 main pieces initiated a critical, irreversible time window. For 72 years, the Northrop A-17A Nomad existed in a highly stable environment. Deep, cold freshwater inhibits severe galvanic corrosion, preserving thin aviation aluminum far better than a saltwater marine environment. The freezing temperatures and low oxygen levels essentially freeze the material degradation rate, establishing a strict freshwater baseline state. However, the exact moment the airframe is hoisted into the open air, this protection is instantly stripped away. Atmospheric oxygen mixes with the moisture trapped in the sediment and the corroded crevices of the metal. If the structure is allowed to dry out naturally in the sun, this combination immediately accelerates rapid oxidation. The aircraft goes from a dormant state to aggressive chemical decay in a matter of hours. To prevent this destruction, the engineering team had to implement immediate stabilization protocols the moment the barge crane secured the load. The 5 major sections could not simply be left exposed on the deck of the recovery vessel. The dense mud that had encased the heavy radial engine and the shattered fuselage was now a hazardous moisture trap. The crews had to immediately wash away the silt and apply protective wet treatments to the exposed surfaces. The metal had to be kept chemically neutral. The operational focus shifted entirely to managing the physical transition of these distinct wreckage sections from a submerged environment to ground transport. Every fractured wing root and sheared bulkhead had to be supported on custom wooden cradles to prevent the weakened, 70-year-old aluminum from collapsing under its own dry weight. Once stabilized on the surface, the recovery operation officially concluded its marine phase. The Royal Canadian Air Force Engineering Squadron prepared the fragmented components for overland transport. This required loading the radial engine, the isolated starboard wing, the shattered port wing, the severed tail section, and the heavy undercarriage onto specialized flatbed trailers. Securing these fragile shapes for a highway journey required precise tensioning of the transport straps to avoid crushing the hollow aerodynamic structures. The destination for this convoy was the National Air Force Museum of Canada. This transfer marked the final logistical handover of the aircraft. The military personnel had successfully executed the physical extraction from the lakebed, and the responsibility for the airframe now shifted from the recovery engineers to specialized historical conservators. Upon arriving at the National Air Force Museum of Canada, the aircraft entered a long-term controlled environment. Inside the museum, conservation began the only safe way: wet, clean, and slow. The heavy radial engine required intense manual cleaning to remove the packed silt from deep inside the cooling fins and the cylinder heads. If this organic material was left inside the engine block, It would trap moisture and rot the steel components from the inside out. This slow, a highly disciplined process forces the trapped water and corrosive agents out of the aluminum pores without warping the thin metal skin. The conservation process is not a rapid restoration designed to return the aircraft to flying condition. It is a methodical stabilization effort designed to freeze the degradation process permanently. By halting the corrosion cycle, the museum ensures the physical evidence of the 1940 mid-air collision is maintained exactly as it was recovered from the mud. The successful recovery of Nomad serial number 3521 represents a triumph of operational discipline over severe environmental constraints. The initial early 1940s search ended in human failure due to the rigid physiological limits of early deep water diving. 7 decades later, the modern extraction succeeded because every step was walled off, documented, and executed in order. The meticulous transition from the deep, cold water baseline to a long-term dry conservation facility prevented the rapid decay of the historical aluminum. This highly controlled handover resulted in the measurable preservation of one of the very few surviving Northrop Nomad A-17A airframes, maintained as recovered evidence of a 1940 mid-air collision.